Hello everybody, getting ready to do lesson chapter 11, review and summary, classwork lesson, part 1, pre-calculus math. And for today's lesson, we have chapter 11 summary. You have 0 points going to your notebook, and this is a classwork lesson. You got 60 points, will go onto your classwork sheet, which you should have out in front of you now. Name, date, period. Due date here for onliners and homeschoolers. And page, we go into our bell work. Students and teachers, we go into a bell work here. True and false, justify your answer. 106, 107. If the degree of the numerator n of x of a rational function f of x equals n of x over d of x is greater than the degree of its denominator d of x, then the limit of the rational function as x approaches infinity is 0. Is that true or false? And then the expression f prime z gives the slope of the tangent line to the graph of f at the point z, f of z. Is that true or false? Teachers, give your students about 3 minutes. They should know this. So pause it, see you in 3. Okay, welcome back. Here's the solutions here. The answer is false. The limit does not exist for here as x approaches infinity is 0. Is that true or false? The limit would not exist when you have a situation where the numerator of a rational function is greater than the degree of the denominator. The limit would not exist in that situation, and students, you should know that. And down here, true, the derivative of f at a point is the slope of the tangent line to the graph at that point. Therefore, at z, f of z, the derivative is the f prime of z. Okay, going into our first part of our review here, using properties of limits and direct substitution. This is for 11.1. to evaluate limits. So what do we have here? Let b and c be real numbers and let n be a positive integer. So here are rules of limits here. The limit of b where x goes to c equals b. The limit of x as x goes to c would be c. And then the limit of x to the nth power as x goes to c would be c to the nth power. And then number 4, rule would be the limit as x goes to c of the radical x to the nth index would equal the nth root of c is what it would be for n even and c greater than 0. So that would be your 4th rule there of limits. And then properties of limits for 11.1, let b and c be real numbers, let n be a positive integer, and let f and g be functions where the limit as x goes to c of f of x would equal L, and the limit as x goes to c of g of x would equal k. So b and c are real numbers in this situation. Let n be a positive integer, and f and g be functions where this is a situation here. And then number 1, the limit as x goes to c for b of f of x bracket would be BL in this situation. BF of x as x goes to c would equal BL. And then the limit as x goes to c of f of x plus or minus g of x would equal L plus or minus k. Then rule number 3 here, properties, would be the limit as x goes to c of f of x g of x would equal LK. And then the limit as x goes to c of f of x over g of x would equal L over k. And then the limit as x goes to c of f of x to the nth power would equal L to the nth power. So let's try one now. Use the given information to evaluate each limit. So for number 9, And this goes down here. This is yours down here, students. We're going to do the guided practice in class now. So the limit as x goes to c of f of x equals 2, and then the limit as x goes to c of g of x equals 5. So knowing that for a and b here, we have x to c, the limit as x goes to c of f of x to the third power. What would that be? And for that one, it'd be f of x to the third power would be 2, because we have f of x equals 2 as x goes to c. So it'll be 2 cubed would equal 8. And then down here for 3 times f of x minus g of x would be 3 times 2 minus 5 would equal 1. So that would be your limits for that. And then down here, I guess is your lucky day, students. I go ahead and throw this in. That'd be 2 times 5 would equal 10 for C. And then for D here, f of x over g of x would be 2 over 5. Into 11.2 now. Use the dividing out technique to evaluate limits of functions. So using that technique, when evaluating the limit of a rational function by direct substitution, you may encounter the indeterminate form of 0 over 0. So sometimes that'll happen. And in this case, factor and divide out any common factors first. Do that first. Then try direct substitution again. And this was in examples 1 and 2. For 11.2, we covered that in classwork. So, okay, let's try 1. Find the limit. If it exists, use a graphing calculator to confirm your result graphically. So we have a limit here as t goes to -2 for t plus 2 and t squared minus 4. In our guided, this is your independent down here, students. So for the guided, as the limit as t goes to -2 for t plus 2, t minus 2 over t plus 2. And then when we factor this out, we have 1 over t minus 2. And then as t goes to -2, this would be -2 minus 2 would be a -4. So it'll be 1 over a -4, or the -1/4. Then going on now into 11.3, which we covered. Find the derivatives of functions and use derivatives to find slopes of graphs. So the derivative of f at x is given by our difference quotient here. Here's our f prime x. As h goes to 0, will be f of x plus h minus f of x over h, provided this limit exists. The derivative f prime of x is a formula for the slope of the tangent line to the graph of f at the point x, f of x. So this is kind of the rule you can kind of go by. This is kind of like the verbalization of what the difference quotient does. Okay, so find the derivative of this function here, f of x equals 5. So for that, what we have here, we use our difference quotient here, and we come up with f of x equals 5, and then minus f of x, be 5 minus 5 over h would be 0. So your derivative for this would be a 0. Moving on now into 11.4, find the limits of the sequences. So a limit of a sequence, let L be a real number, let f be a function of the real variable, such that the limit x as x goes to infinity of f of x equals L if an is a sequence such that f of n equals an for every positive integer n, then the limit as n goes to infinity is an would equal L. Okay, so there's a lot of technical language there. So let's try to put some of that into practice here. Write the first 5 terms of the sequence and find the limit of the sequence if it exists. If the limit does not exist, explain why. Assume n begins with 1. So with those kinds of limits here, we have an equals 2n minus 3 over 5n plus 4. And to find that, here's our initial expression. Then if we go with a1 would equal -1 over 9, a2 would be 1 over 14, and etc. here. As it goes to infinity, it will become actually 2 over 5, and you could find that if you graph this in your graphing calculator, it will be 2 over 5. And then this is yours down here, students, so do that. Then we go in now to 11.5. Use rectangles to approximate and limits of summations. To approximate and limits of summations, you were going to use rectangles to approximate and find the limits of summations to find areas of plane regions. So a collection of rectangles of equal width can be used to approximate the area of a region. Increasing the number of rectangles gives a closer approximation. And see example 5 and 11.5. I'm sorry, example 4 and 11.5. The area of a plane region, let f be continuous and non-negative on AB. The area A of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by, and here it is. Here I have this gnarly summation here of as n goes to infinity for n and I equals 1, and then we have the function of this here, of this formula here, which you learned in 11.5. We did that in classwork, and we did it in our homework. Use the limit process to find the area of the region bounded by the graph of the function and the x-axis over the specified interval. So here's our interval here, f of x equals 6 times quantity x minus x squared. So to find that area over that interval, we use our formulas that we have for summations, which is up here, f of I to the n over 1 over n. And then we pull our 6 out here out in front with the n, and then we have in minus in squared multiplied by 1 over n. And then we pull this out here too as well out in front. Then we're left with that. And then these transfer into these kinds of expressions here. 1n times n plus 1 over 2 minus 1 over n squared multiplied by this becomes n times n plus 1 times 2n plus 1 over 6. That would be your basic setup there. And then students, you're going to continue that down here in your independent practice to find what the actual area is of that. But you have this rather elaborate kind of setup here that's derived from these two elements here that are translated over into the formulas for finding area. And that is your Chapter 11 review and summary classwork for pre-calculus math. Animated PowerPoint math video at AOL.com for course materials and or questions. Thank you very much.